Hi, welcome to the next chapter of trigonometry, and we're looking at section 5.1, verifying trig identities. So first we'll start out with just listing some of the old identities that we have memorized that we're going to be using. So let's take a look at those. Okay, so these, I'll just call these the fundamental identities. And it's my belief that you kind of already have these somewhat memorized, maybe not all of the even odd functions, but everything else you should sort of have memorized. So the reciprocal identities, and you may want to fast forward. I'm just going to be kind of going over things that you may or may not know. So anyway, sine x and cosine x. Sine x is the same as 1 all over cosecant x. Cosine is the same as 1 all over secant x. And then, of course, we have tan x is 1 over cotan x. And then, cosecant x is 1 over sine x. And secant x, of course, is 1 over cosine x. And finally, cotan x is 1 over tan x. Okay. Along with those, we always have the quotient identities then, and that only really applies to tan and cotan. So tan x is equal to sine x over cosine x, and then cotan x is equal to cosine x over sine x. Okay, so those you should know. The Pythagorean identities, you also need to know. Pythagorean identities. Let me just make sure I'm recording as usual. Yeah, I'm good. So the Pythagorean identities, this starts with the sine squared x plus cosine squared x is equal to 1. And then if you divide everything by cosine squared x, you get 1 plus, you get tan, right? Sine over cosine. So you get tan squared x. Cosine squared over cosine squared is just 1. And then 1 over cosine will give you secant squared x. Then if you divide the original sine squared plus cosine squared equals 1 by sine squared, you end up with 1 plus cotan squared x equals cosecant squared x. Okay, so you should know all those. Then the last ones you're probably not as familiar with, even though we've kind of just learned about them, the even and odd functions. So, I remarked that we basically focused on cosine and sine and maybe tan. But cosine is really the only even function. So if you put a negative x inside of cosine, you'll end up with just cosine. Okay. Then it's secant. The secant function is the same. It's even, just like cosine is even. And then the rest are all odd. Okay. So the rest of them, we have. Just try to sort of list them out here. Sine of negative x, tan of negative x, cosecant of negative x, and then cotan of negative x. Because these are odd, you'll just end up with a negative on the outside. So negative sine x, negative tan x, negative cosecant x, and then negative cotan of x. Okay. So these are the only even ones, and then everybody else is odd. Okay. And it really has to do with another way of thinking of it is just the symmetry of the graph. If it has a y-axis symmetry, like the cosine function, it's the same on both sides of the y-axis. Okay. For odd symmetry, it has origin symmetry. So this point here, if you have a point x, y, then you'll also have the point negative x, negative y on the graph. So like cubic functions have odd symmetry, and then the tan functions will have odd symmetry. I mean, the tan function almost looks like a cubic. X cubed, right? It almost looks exactly like it. So those guys are all odd. Anyways, just trying to give you some way of memorizing that. Anyways, what we want to do in this section is to verify identities. Section 2, verify identities. And so people often get this confused with kind of solving equations. They think verifying an identity is the same as solving an equation, which is it's not. The way you verify an identity is you kind of work on one side and you work on the other side, kind of separate. Okay, so this is it's not. What is it? Well, I could tell you what it's not. It's not like solving an equation. Okay. So an example, you would have something like 2x minus 5 equals 3 plus x, right? And then you would get subtract x from both sides, you get x minus 5 equals 3. Then you would add 5 on both sides, you get x equals 8, right? So it's not like solving an equation. And so what really makes it different is that you're not moving stuff from one side to the other, okay? So it's not like solving an equation. In other words, you can't move stuff using the equation properties. The add something to both sides, multiply something on both sides, take square roots on both sides. You can't do any of that stuff here. So you can't move stuff from one side to the other. In other words, you really have to move. You have to work on either side separately. Okay. Have to keep the sides separate. Okay. So let's take a look at what we're up against, okay? And when you do your proofs, there may be some scratch work. You may have to fiddle around with it at first, and that's like a rough draft. And then ultimately you'll write up your answer the way I'm writing up my answers here. Okay, so what I definitely don't want to see is something like that red example there. That's bad news. This is bad. Trying to solve it like an equation. We want to avoid that because what you've assumed is kind of what you're trying to prove in a weird sort of way. So you've kind of assumed that it's a true identity in that first line, and then okay. So let me show an example, and hopefully we'll start converging to kind of the method. And you can follow along in your book. This is checkpoint 1 in this chapter. So they have all those little checkpoints to help you check your work. So we want to verify the following identity. And, those are the directions. Verify the identity. And what they're giving you looks like an equation, but it's not. Okay. Cosecant x, and that you don't want to solve it. Okay, I mean, yeah, it's an equation. There's an equal sign there, but you don't approach it like an equation. Okay, you have to kind of work on one side and the other side separately. So verify this identity, and what I usually do is just start on the more complicated side. So that left side has more junk on it, right? And the right side just has one thing there. The left side has two things there. The right side has one thing. So I'm going to start on the left side. So start on the left side, and notice the following. So You start with cosecant x, so you just rewrite the left-hand side, and then we do substitutions with our identities back here until we can produce the right-hand side. Okay, and this is kind of where it takes a bit of guesswork. Sometimes I've had problems, believe it or not, where it took a whole page, and at the end of the page I just got back to where I started. I was never able to get to the other side. Okay, so yeah, sometimes it's going to take a bit of work and a bit of guesswork, but yeah. Okay. So, anyways, let's get in here. So one identity I can do is to just rewrite these in terms of sines and cosines, and that makes it more familiar, right? So I can rewrite cosecant as 1 all over sine x, and then I can rewrite tan as sine x over cosine x. Okay. And then that simplifies, right? The sine x over sine x, I can remove that. That's just 1 over 1. And then I can multiply straight across, and I get 1 over cosine x. And then 1 over cosine x using my reciprocal identities, what is that? Well, that's secant x. And that's exactly where I want to end up. Okay, so I guess I got lucky here this time. And then you have to tell, that's where we wanted to, or what we wanted to show. Okay, or just say which is the right-hand side. So you have to imagine that there's somebody reading your work and that you're explaining it to them. I think my sort of, why would I care about explaining my work? It has to do with artificial intelligence. So this may sound kind of crazy, but it turns out that with artificial intelligence, some of the solutions that computers find for answers, we don't necessarily understand how they got the solution, believe it or not. So me personally, I think if we focus more in our education about teaching people how to explain what they're doing, hopefully when they go and make their artificial, so when you guys go eventually, if some of you become pure programmers or whatever, you'll kind of code in the explanations to what's going on. It's not just this kind of random, here's a bunch of stuff and somehow I magically got the answer. No, we want it to be readable and understandable, so we're not, we're not dealing with like artificial intelligence that's doing something we don't understand. I mean, that's one of the big issues, right? We're afraid of artificial intelligence kind of taking over and like if you ever saw the movie Terminator, right? And it sounds crazy, but it is kind of, okay. So anyways, there's that. Okay, so we did our first verify the identity. And note, I did not like divide both sides by tan, going back to the actual identity. I didn't try to subtract secant to the others. No, you start purely on one side or the other. In this case, I just picked the more complicated side, and then you use identities and do substitutions until you can get the other side, okay? And that's it. That's pretty much the idea in a nutshell. Let's look at some more problems, right? So a lot of these, like I said, sometimes you'll just have to kind of spin your wheels for a little bit, but I think it's kind of cool when you actually figure it out, and I don't know. So anyways, let's look at the next one. So again, it's verify the identity. Here we have sine of x, tan of x, plus cosine x equals secant x. Okay. And again, I'm going to work on one side and then get on to the other side. And sometimes it's not even, it's so complicated, you have to kind of work with the two sides separately. And I'll show you an example of that at the end. That's like, we hope we don't have to do those kinds, right? Okay, so anyways, verify the identity. And so I'm going to start on the left again, because that's a big mess right there. So start on the left and note and notice the following, right? So and note, and then I just rewrite it. So sine x tan x plus cosine x, and then use some identities. Well, one thing, I notice is I need to turn two things into one thing. So somehow, somewhere, I'm going to have to be able to do that. If nothing else, we can always rewrite tan in terms of sines and cosines and go from there. So here we go. Sine x times sine over cosine, right? Sine x over cosine x plus cosine x. I could turn this thing into a fraction again. So that should just be sine times sine of sine squared over cosine x. So I get sine squared x over cosine x plus cosine x. I want to end with one term, right? So on the right, I got one thing. So well, I have to combine these two, right? And one way I can do that is by finding a common denominator. So that cosine x is the same as cosine x over 1. And if I want a common denominator, I just multiply top and bottom by cosine x. Okay, so then that will equal sine squared x over cosine x, and then plus the result of that, finding the common denominator, I now have cosine squared x all over cosine x. Then I can add the two numerators over the common denominator, and your familiarity with those identities really will pay off in this section, right? Because you may see that, well, that's sine squared plus cosine, that's the Pythagorean identity. That's just equal to 1. So I could substitute 1 in for sine squared plus cosine squared, and I get 1 over cosine. And then 1 over cosine, well, hey, that's just secant, right? Which is what I wanted to show. That's the right-hand side. So finish off the kind of statement with something that tells the reader what you've just done. It's the right side of the identity, and once you show the left-hand side and the right-hand side are the same, you're done. Okay, and that's what we did there. Okay, let's do another one of those checkpoints. So here's checkpoint 3. And I've done all these problems beforehand, so you don't see me like struggling, but you're going to struggle when you do. It's not going to be easy at first. You got to get some practice. But I promise it gets easier over time. Verify the identity. I mean, you're always going to have your struggles, but this particular struggle will not be so bad. It's not going to be something to haunt you. Anyways, here is the identity we want to prove. Again, it looks like the left is the more complicated side, so I'm just going to start there. So starting on the left. So please write that out. Starting on the left, tell me what side you're starting on. We note sine x minus sine x cosine squared x equals. So the first thing I notice is both of these terms have a factor of sine, which I can factor out. And then you're just left with 1 minus cosine squared x, which is awesome because then that's kind of a Pythagorean identity, right? So the Pythagorean identity, sine squared x plus cosine squared x equals 1. Certainly we know that, but we should also kind of be familiar with the manipulated versions of these. So if you subtracted cosine squared from both sides, you kind of make it a whole new identity from that original identity, which is true. So you can't in general do this in proofs, but here, once we have it established that sine squared plus cosine squared is equal to 1, then you can sort of start pushing things to the other side, and you're still going to have a true statement. But here, look, you have a substitution for 1 minus cosine squared. That's just sine squared. Okay, so you could take that and put that in to our expression. So you have sine x times sine squared x. And then you have basically 3 factors of sine. If you multiply them all out, you get sine cubed x, which is the right-hand side, which is what we wanted to show. Okay, so once you've done that, you're done. Okay, let's do another one. This one we're going to do it in 2 different ways. Okay, and this is going to be the video quiz. All you have to do is basically reproduce this thing. Let me make a note here in my notes. Okay, so this will be the first video quiz problem in this next set. So 5.1. It's example 4 from the book. And when you write up your answer for your for the homework submission, make sure you put both methods, because we're going to do it in two different ways. Okay, so there's more than one way to do some of these problems. So example 4 then, this is the video quiz question. Okay, so verify the identity 1 plus sine theta over cosine theta equals secant theta plus tan theta. Okay, so method 1. This time I'm going to start on the left-hand side, so starting on the left, I note. And what you could do is kind of take this expression, 1 plus sine theta over cosine theta, and butterfly it, right? Because ultimately on the right, we want two separate things, and we have one thing here. So it's kind of intuitive. All right, well, I can separate this into two fractions and then kind of just see what you get, right? Okay, so starting on the left, I note this. I can separate it into two fractions. It's basically just the reverse of finding a common denominator, right? And then you could use reciprocal identity and quotient identity to rewrite that. So 1 over cosine is just your secant theta. Sine over cosine is just your tan theta. And already we got it, right? That's our right side. And we're done. Okay, so that's the first method. Let's look at a different method. And the deal here, I'll just start, I haven't had to do this yet, but I'm going to start on the other side. Okay, so maybe you looked at that expression and you thought the right-hand side was more complicated. Okay, and you could start on that side. So that's what I'm going to do. Start on the right and note, so I'm starting this time with secant theta plus tan theta. And then I'm going to rewrite it using quotient and reciprocal identities. 1 over cosine theta plus tan is sine theta over cosine theta. And those two fractions have a common denominator, so you can combine them and add the numerator over the common denominator. And lo and behold, what you get is the left side, right? So then you're done, which is the left side, which is what I wanted to do. That's what I wanted to show. So you're done. Okay, so that's the video quiz question. You got to show me both methods in the homework. Okay, let's move on. So I'm just trying to do as many examples as I can. And like I said, when you go to do it, it's probably not going to be as nice and easy as what I'm doing, because I've done all the problems before, you know, and I've taught the class and before, and it's just you're just going to have to work a little bit. And then, you know, your work, when you actually do it in a test, and the tests aren't like computerized this time around, but the test is well, the last test was handwritten, and maybe this one's computerized. I have to look at my syllabus. I think maybe this one, maybe I should do all of them just handwritten. I think I might just do all of them handwritten. So anyways, there's that. Starting on the right side, and we show that's okay. Let's go on to another one. Checkpoint. This is checkpoint 5, and we want to verify the identity again, as usual. Given as sine x all over 1 plus cosine x plus 1 plus cosine x all over sine x equals 2 cosecant x. Okay. I think that this one clearly is just like start on the left, find some common denominators, and hopefully turn it into one term. Okay, so that's what I'm going to do. I'm going to starting on the, not the left, but the right. No, that's the left. I'm right. So starting on the left, I note, or we note, or whatever you want to say, sine x all over 1 plus cosine x plus 1 plus cosine x all over sine x. So first I'm going to find a common denominator. So on the first fraction, I need to multiply top and bottom by sine x. And the second fraction, I need to multiply top and bottom by 1 plus cosine x. Okay. So, let's see how that pans out. Just got to get my other marker. Okay, so in the first fraction, you're getting sine squared x. In the second fraction, all over, you know, your 1 plus cosine x times sine x. Plus, in the second fraction, you could FOIL that thing out. You know, you have 1 plus cosine x times 1 plus cosine x. That'll end up being 1 plus 2 cosine x plus cosine squared x. And then that's all over our common denominator, sine x times 1 plus cosine x. Then you could combine the numerators over the common denominator, and you get sine squared x plus 1 plus 2 cosine x plus cosine squared x all over the common denominator, sine x times 1 plus cosine x. Okay. And then you can see that if you rearrange the terms, and you don't necessarily need to rearrange them, but if you need to rearrange them so you can see it, there's a sine squared plus cosine squared identity, right? You could replace those two guys with 1. So let me just rewrite it. Sine squared plus cosine squared. You don't need to do this step, but I'm doing it for your benefit, just so you can see what's going on. Okay, so this part, again, this part you could do a substitution, right? That's just equal to 1. So it's 1 plus 2 cosine x all over sine x times 1 plus cosine x. And then 1 plus 1, of course, is 2 plus 2 cosine x all over sine x times 1 plus cosine x. And, you know, kind of keep in mind where you're headed. We want to get a cosecant out, which is 1 over sine. And I think we can get a cancellation, right? Because in the numerator, this thingamajig, 2 plus 2 cosine x, is basically just a multiple of 1 plus cosine x. Right? You just factor out the 2, and you see there's a nice cancellation. So you can remove the 1 plus cosine x's, and then you're just left with 2 over sine x, and we, you know, we want to end up at 2 cosecant x, and that's our goal, and of course that's where we're ending up. So this is the same as 2 times 1 over sine x, which is 2 times cosecant x, okay, which is what we wanted to show. It's the right hand side, right? Okay, so make sure you write that. Let your human reader know what you're doing. Okay, so which is the right hand side. RHS is right hand side. Okay. Okay. Let's do another. So we'll just do 2 more, and then I'll show you one of those weird ones where we kind of can work on the sides separately. So anyways, verify the identity. As usual, this time we have sine of x all over 1 plus cosine x equals 1 minus cosine x all over sine x. Okay. Okay, so this time I'm going to start, believe it or not, on the left. And note, I'm going to show you some little clever trick that you may not think of doing, but is perfectly legal. And where I want to end up, you know, is also in my brain as I kind of go through these. Where I want to end up is on the right with the denominator is just sine x. Okay, so right now in the denominator I have 2 things, right? I want to end up with a denominator that just has 1 thing. So what's one way I can go about doing that? Well, you can actually multiply top and bottom by something. You could multiply it by anything in top and bottom, as long as it's the same on the top and the bottom, right? So here, And this is where it's kind of like you may not have ever thought of doing this, but you can multiply by what's called the conjugate and top and bottom. And so we'll have sine x times 1 minus cosine x up top. But in the bottom, what do you have? You'll have, if you FOIL it, 1 times 1 is 1. Then you'll have plus, or outer, right? So minus cosine x, the inner plus cosine x, those cancel. And then the last cosine times negative cosine is negative cosine squared x. Okay. So what? Well, 1 minus cosine squared x, if you've forgotten, is sine squared. So we have equals 1. So if I move the cosine to the other side, we could replace 1 minus cosine squared with sine squared. And then you can cancel that with the numerator, right? Because there's a factor of sine in the numerator. So we have sine x times 1 minus cosine x all over, I could do a substitution, get sine squared x. And then we can remove one factor of sine, right? So you end up in the numerator with 1 minus cosine x, and the denominator you have that one thing, just the sine x. And that turns out to be where we want it, right? That's the right-hand side. Okay, so it's a little bit, it's kind of has like a kind of a, I don't want to say it's an art form, okay? Because you could really, I believe you could probably program a computer to do these kind of simple verifications, but it is for us humans at first. It's kind of an art form. You know, it feels like, you know, there's no set protocol, no method that at least you're aware of. But after a while, you get into it. There's only so many different things you can do. And you would try each one. If you were more thinking in as a computer, you would just go through the list and try each one until you can transform it into whatever you're trying to transform it into. So I don't know. In the beginning, yeah, it feels like you're learning how to do art. You're spinning your wheels sometimes. Sometimes you're not going to get the answer. So yeah. Okay. And I mean that's an important topic in like science, computer science. Is are these things kind of like programmable? Is there anything which is not programmable? Is there anything that we as humans can kind of do that maybe a computer can't do? It's that big. That was like a big question for the past 100 years. Okay, with all the computer science stuff. Anyways, let's move on. I'm just hoping, sometimes with math, it gets so abstract and so far away from real life. You kind of want to, introduce reality back into the math. And the easiest way for me to do that is just thinking about how computers work and how they think. So anyways, let's look at another one, checkpoint 7. This uses some of the even odd identities. We haven't seen that yet. So verify. This will be the last example we look at, and then I'll do one of the weird ones where I kind of work on the two sides separately. So anyways, verify, again, the following identity. And we have secant x plus cosecant negative x all over secant x times cosecant x. And we want to show that that's the same as sine x minus cosine x. Okay, so I think what I'm going to do, obviously, if you just counted up the little symbols on the left, you have more symbols, okay, than you do on the right. So I'm going to start on the left. So starting on the left, I note, so give the reader some direction of what the heck it is you're doing. Secant x plus cosecant of negative x all over secant x, cosecant x. I want to split this into two fractions, but first I kind of want to still, deal with this critter right here using the even and odd identities. So everything is basically odd except for cosine and secant. So we can replace this with negative cosecant x. So I'll have secant x minus cosecant of x all over secant x cosecant x, and then you could take the fraction apart and by butterflying it, or some people like to say fillet it, like you would fillet a fish. So you end up with secant x all over secant x cosecant x, and you get some nice cancellations, minus, not equals, minus cosecant x all over secant x cosecant x, and you see those nice cancellations. Boom, 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 boom. End up with 1 all over cosecant x minus 1 all over secant x. And, you know, where are we trying to end up? Sine x over cosine x. That's what we got, right? So 1 over cosecant, that's one of our reciprocal identities. That's equal to sine x minus 1 over secant. Another reciprocal identity is cosine x. Cosine x. And I think that's what we wanted, yeah. So sometimes I sort of cover up the answer because you have like self-fulfilling prophecy type things going on psychologically. Like you kind of, even if you don't have the answer, you'll just kind of like skip to it somehow. Like one thing you can't do in proofs like this or verifications like this is you can't like just, you know, I don't want to see on a test you skipping from here to here, right? You got to show those steps so your reader knows what you're doing. Anyways, starting on the left side, I note all this rigmarole, which is the right-hand side. Okay, so let's look at one where it's kind of like a lot harder, and maybe you need to work on the side separately first. Ultimately, you can always, though, rewrite it in one of these going from left to right forms. It's just it may be easier to kind of work independently and join the two sides together. That's kind of, I think that's how they built the channel that goes from England to France under the channel there. The French dug on one side and the British dug from the other side, and they met in the middle. So you can kind of do it that way. One thing, again, you don't want to do is work it as though you're solving an equation. Okay, you can't do that because you've assumed something that may not necessarily be true. For example, if you assume that 1 equals 0, if you start there and assume it's true, you can always do crazy stuff like add 1 to both sides. 1 plus 1 is equal to 0 plus 1. And then because 1 equals 0, you could say, ooh, this is 1 plus 0 equals 0 plus 1. And then you end up with a true statement. You know, 1 plus 0 is 1. 1 plus, hey, it's true. I just showed it. So you get in all these weird sort of situations that you just avoid the heck out of it. Don't work on like equations, okay? Work on one side and, you know, go to the other or do a channel sort of situation. And even when you do a channel, you kind of, at the end, it needs to be readable, you know. So anyways, let's look at one of these. So this is example 8 in the book. And we're trying to, you know, we're verifying identities as usual. Verify the identity, this time 1 all over 1 plus cosine theta. Plus 1 all over 1 minus cosine theta. And supposedly we want to show that this is the same as 2 plus 2 cotan squared theta. Okay? Okie dokie. So first, let's say I'm just randomly kind of guessing. I think the left is a little more complicated, right? So that'll tell my reader I'm starting on the left. So starting on the left, I notice the following. Notice, oh, that's not even the word notice. It's noti. I notice. Okay. Starting on the left, I notice 1 all over 1 plus cosine theta plus 1 all over 1 minus cosine theta. Okay. You know, my instinct is to find a common denominator is usually kind of how I do it. So on the first fraction, I'll multiply top and bottom by its conjugate, which is basically the denominator in the second fraction. So it's 1 minus cosine theta. Make it clear, then I'm multiplying the entire object. 1 minus cosine theta. And then on the other fraction, top and bottom by 1 plus cosine theta. make it clear. Then what do I have? So in the numerator, in the first one, I have 1 minus cosine theta all over the denominator here is 1 minus cosine squared theta. So first outer, inner, last, the inner and outer will cancel. Plus 1 plus cosine theta all over 1 minus cosine squared theta. First outer and last. Combine the numerators of the common denominator. So 1 minus cosine theta plus 1 plus cosine theta all over 1 minus cosine squared theta. And then it looks like the cosines will cancel, and you'll have 1 plus 1, which is 2, all over 1 minus cosine squared theta. Okay. Let's say I don't know what to do next. Okay. Let's just hypothetically, let's say that, you know, I'm kind of stuck. I don't know how to get from the 2 over 1 minus cosine squared to 2 plus 2 cotan squared. It's just no clue. So what do? Well, start on the other side. Okay, so say, okay, I'm going to starting on the right and work there independently and see if you can at least kind of build a channel to the 2 over 1 minus cosine squared theta. Because if I can get there, then the two sides will be connected and I'll kind of done my job. Okay, so starting on the right, I note what? Well, what is the right-hand side? 2 plus 2 cotan squared. 2 plus 2 cotan squared theta. I could factor out a 2. Okay, so I can factor out a 2, and I have 1 plus cotan squared theta. Then 1 plus cotan squared, that looks like one of the identities, right? From one of the Pythagorean identities from way back when. So our Pythagorean identities, you know, you may have to go back and kind of re-engineer them. Hopefully you know this one. Cosine squared plus sine squared is 1. If you divide them all by cosine squared, you get tan squared plus 1 is secant squared. That's not going to help. If you divide them all by sine squared, you get 1 plus cotan squared. That's the one we need, right? So I can do a substitution for 1 plus cotan squared, and I end up with 2 times cosecant squared theta. Okay. Where am I headed? I'm trying to get a fraction, so let's turn this into a fraction using reciprocal identity. So that will be 2 times 1 over sine squared. Well, in other words, 2 over sine squared, because cosecant is 1 over sine. And then I'm almost there, right? I almost built the channel. I just need to get sine squared and the 1 minus cosine squared, and I can do that via substitution from the Pythagorean identity. Sine squared theta, if I just subtract cosine squared from both sides, I get 1 minus cosine squared. Okay, so I can rewrite this as 2 all over 1 minus cosine squared theta. And what I've done is connected, I've built the channel. Okay, which is it's kind of like a transitive thing. So maybe I should say, so we note from sort of our first part from above that 1 over 1 plus cosine plus 1 over 1 minus cosine equals 2 over 1 minus cosine squared. So I note from above 1 all over 1 plus cosine plus 1 all over 1 minus cosine is equal to 2 all over 1 minus cosine squared theta. And then from the second kind of part where I started on the right, I can say that that part is then equal to 2 all over, you know, I've connected the channel, right? So that's then equal to, well, this side, it's equal to the, eventually if you just go, you know, in reverse over the here, you get back to 2 plus 2 cotan squared theta, which is, I mean, that's what I wanted to show, right? I wanted to start on the left and then go to the right. You could write it all out, but, you know, why bother? We kind of have it there above, and I think I hope that's clear. If not, you can literally write out all the little steps. right? But I wouldn't do it. I would just copy and paste it all. So I would go like, all right, I'm going to cheat a little bit here, which you can't do, but I can do it pretty easily at this point. Jeez. Yeah. Oh, come on. Okay. And then I just take all this baloney. Oh, and of course it's not going to let me. It's going to let me, but it's going to make me do it really, really slow. So if you wanted the foolproof, you can kind of stop there, and then you're just borrowing this junk, right? But you kind of have to do it in reverse, so that doesn't work so well. Oh, man. So, yeah. You'd have to kind of re-engineer. So I'm sorry, that doesn't work out very well. So let me just get rid of that. Oh, man. I'm going nuts. Okay, so there's that. Anyways, hopefully that made some sense. And then, of course, I just erased everything I needed. So the problem is you got to make this readable, right? You got to make it so somebody else will understand it. It all goes back to, we don't want artificial intelligence getting carried away and doing things we can't understand. So you want to kind of program the computer to be able to explain it to the human user. This would be my motivation behind the scenes for being able to explain this, as opposed to just throwing a bunch of random stuff on the screen for your teacher to figure out or whatever. So we had start. I wonder if I can kind of redo things. Oh, well I got it back. The magic of the computer. All right, there we are. So starting on the left, I got to here. Then starting on the right, I got to the same place. So therefore, I can connect the two from above, and that proves the identity. So I'll just say which is what we wanted to show. Okay. Writing in black, which is what we wanted to show. So for you, if that became the situation, I mean, normally on a test, they're not going to be that hard, and you're just going to be able to go from the left to the right. Okay, but say on a test, or maybe on a homework, I did have one like this. How would you show it? This would be good enough. Start on I would understand that. Start on the left. I notice that it's equal to this. I'm starting on the right, and I find that it's equal to the same thing. I built my channel, therefore from above, the two sides are equal, and that's what I wanted to show. Okay, so hopefully that's clear. Like I said, I wouldn't put a harder one on the test. You should always just be able to go from left to right, but you need to be able to explain it. You can't just kind of randomly throw a bunch of symbols up and then, hey, here's my proof. Okay, now I need a little bit more in that. Your future generations need a little bit more than that from you. Okay, so we'll call it quits for now, and thank you for watching, and we'll see you next time.